well, what we saw last time, to recall, was we introduced, the functors and sheaves on sites. And today we're going to sort of go over here and discuss groupoids and prestacks. But I would like to kind of give a review of what we covered last time. And partly because the first two lectures were a lot of motivation. I was trying to motivate sort of the approach that we're taking in the class. And I was hinting at a lot of concepts that we're going to use, such as descent, art approximation, and the functorial perspective. But I'm not going to develop those systematically in the course, and rather point to other references where you can learn about that. But the two things I did introduce formally, and that they're important, what was the definition of a site and the concept of pre-sheaves and sheaves on that site. So let me recall this definition. So a site, has the data of, first and foremost, there's a category, which we'll denote as S, and then you have, for each object in this category, you have a set of coverings. And here, just to spell out this definition within a definition, a covering of U is is a set of maps, which you read as UI to U, indexed by some set I. And usually, this is the definition. Usually, a covering, this should be surjective in some sense, but yeah. So covering of U is just a set of maps, and then we impose conditions. There was 3 axioms that we require. One is that the identity map is a cover. 2 is that covers pull back. So if I have, a cover UI to U and then a map from V to U, if I take the fiber products, they should exist, and that should be a cover. And then the final condition, which I won't spell out, is that covers compose. And our main example was the big Ital site that you write as schemes and then subscript Ital. And here, the category was just the category of all schemes. And a covering is a collection of Ital maps. Of a scheme U is a collection of Ital maps with the property that, that the disjoint union surjects onto U. And I want to emphasize a special case of a covering is just when it's given by a single map. So here's a special covering is just of the form, maybe UI to U is a surjective Ital map. And it's sort of, and maybe the relationship between all coverings and these special coverings is that, you could always, from a covering UI to U, you could just take the disjoint union of UI to U, and that would give you this. So this is sort of a way to reduce arguments to the case of a single surjective Ital covering. Okay, so that's a site, and this is our main example. And then we had also defined a presheaf, and a presheaf is just a contravariant functor. Say F from the category S to sets. And with that, we say that a sheaf is then a presheaf F such that for all covers, that if you take sections on U should just be obtained by sections on UI via gluing. So this should be exact. And here I'm using shorthand notation that we'll often use. This Uij is Ui cross Uj. And in the case that these UIs are open immersions, for instance, like sort of a site coming from an ordinary topological space, then this Ui cross Uj over U is then the intersection. And to check something as a sheaf, you can often reduce via this to these special coverings. And in fact, you can often reduce even to coverings that are Étale maps of affine maps, Étale morphisms of affine schemes. And maybe let me phrase this as an exercise, isn't particularly hard, but it's useful to work through the notions. The exercise is to show a pre-sheaf F is a sheaf on the big Étale site. If and only if one, it's a sheaf on the big Zariski site. Meaning everything glues with respect to open immersions. And then you just need to check that for all surjections, Étale surjections of affine schemes, that you have the corresponding sequence is exact. And note that, like that if you were to go from like an arbitrary covering on this left-hand side to this special covering, then these fiber products, this like UI cross UI over U, includes all of the pairwise fiber products UI and Uj over U. And also includes you can also, because these maps are not monomorphisms, you need to consider also the self intersection of UI cross UI over U. So this gives you a way to check that pre-sheaves are sheaves. And the one example we had last time that came from descent was we had this proposition that if X is a scheme, that if you take the functor Hx, which was morphisms into X, as a functor from the category of schemes to sets, this is a sheaf in the big Étale topology. That was our main example. So those are the definitions that we introduced, and we introduced them primarily from this perspective of moduli spaces. And let me just also recap how this fits in to our program of introducing moduli. And let's start with F, and let's take a functor, and here I'm just calling it a moduli functor.
Oh, can you try to keep the previous half page visible?
The previous page?
Yeah.
I can go back for a moment, but I can't show both, I think. That would be a nice feature.
Okay. I thought you had been doing that. All right. Never mind then.
Oh, that's right.
One thing that's useful if you're wanting to do this is it's pretty easy to take screenshots as you go along. That's actually probably a pretty useful thing to do if you keep track of what's on previously.
Yeah, thanks, Jarod. I could also upload my slides beforehand, but then yeah, it's more work on my end. Yeah, so these were the definitions. We had sites, we had sites, pre-sheaves, and sheaves. Okay, and now I want to explain this, how this fits into the moduli perspective. And here I'm going to take a functor, and I'm just going to call it a moduli functor. And when I use this terminology, moduli functor, all it means is the sort of informal terminology to mean functor plus you're viewing sort of F of S, that sections over a scheme S as like families of objects over S. So in some sense, I mean, in every functor you can view as a moduli functor where families are just defined to be sections. You know, that's similar to viewing. I mean, every scheme itself is a moduli space parameterizing points of that scheme, right? And specifically, you have the representable functor, which you can view as the moduli functor of points of a scheme. But of course, we're interested in particular moduli spaces, you know, curves and vector bundles. And then what it means for that functor to be a sheaf is that families glue uniquely in the tau topology. And our main example that we saw last time was the functor of smooth curves. So I wrote that as F and G, where to scheme S, you could consider smooth families of curves. Smooth families of genus G curves. So proper smooth, and every geometric fiber is a smooth connected genus G curve. And what we saw last time is that this functor is not representable. And actually, for a similar reason, it's also not a sheaf. And because, you know, we want something to be representable, and what we saw, you know, on the previous page was that a representable functor is a sheaf. So sort of like the sheafiness is maybe the first obstruction or the first thing you want to check if you want to check that you have a representable functor. So representability, or in other words, what we showed on that previous page was that, yeah, representability implies that it's a sheaf. Great. But maybe something I didn't emphasize as much last time is why, in the first place, do we care about representable functors? And let's just suppose, for this discussion, let's just suppose that there exists some scheme M representing this functor F and G. We know there doesn't, but let's just suppose, you know, in this hypothetical world, parallel universe, if it does exist, let's try to say, yeah, what does it give us? And so first of all, what it means is that you have this natural bijection for any scheme S between maps into M and families of curves over S. And so like the argument in Yoneda's lemma, if you take S to be equal to M, then you have the identity morphism on M, and this corresponds to a family of curves over M, which we call the universal family. And so if, yeah, FMG was representable, we would have this universal family, and this is what I tried to draw in the bottom here. So here, this is U, this is M, and M we're thinking of as a moduli space, so points correspond to isomorphism classes of curves. So for instance, C here is a point corresponding to a curve, and then under this universal family, the fiber of that point is the curve C itself. And moreover, sort of being a universal family implies that for all families, say C over S. So if you have an arbitrary family of curves over some scheme, if you take a point here, you know that the fiber is a curve. And so you can define a map from S to M that just sends S to the isomorphism class of that curve. And the point is that if you have this universal family, then actually the family C is the pullback of the universal family. And this is a Cartesian diagram. So that's sort of why we want universal families. And so for instance, if you think about S itself, maybe as a one-dimensional curve, then you're tracing through an arc in the moduli space. And so you can view this as sort of your curve deforming as you move along the base curve. All right, But unfortunately, FMG is not representable. And this is the whole reason why we're going to introduce groupoids, prestacks, and stacks, and so on. So I'm going to turn now to the new material of today's lecture. Well, I'll pause for questions.
Sorry, I have just a small question. Maybe I misunderstood something, but so we discussed in this example last time that the functor, the modular functor, is not representable. I remember that, but why is it not a sheaf? So maybe I didn't see something, but
Oh yeah, I think well, it's for a similar reason. Yeah, it's for a similar. Maybe I'll just say this in words. So imagine. Let me change the color here. Let's suppose you have. I'll just write it in this box here. Suppose you have S, and you have some a tau covering. Or let's even suppose you have a Zariski covering. It's simpler. It's an open covering of some scheme S, and suppose you have a bunch of family of curves over each Si, and then suppose that they agree on their intersections in the sense that, like, if you pull them back to Si cross Sj, then those family of curves are isomorphic. But that's all you know, is that there exists an isomorphism. It's not specified. So if you think about how you glue schemes together, and if you want to create a scheme C over S, you need those isomorphisms on the intersection to satisfy a cocycle condition on the triple intersection. That's required to get gluing, and here we're not specifying that, so that condition can fail. So yeah, that's a reason why it's not a sheaf.
Okay, thank you.
And again, it's coming from automorphisms, because you can, yeah. Great, so yeah, today we're going to discuss groupoids, first of all. So this is first section. And I'm trying to create some sort of balance between, what I write live and what is already written. So hope you bear with me. So yeah, a groupoid is just a category where every morphism is an isomorphism. Yeah, that's all it is. So let's turn to examples. And the first example is going to be Mg of C. And this will be the category where an object equals a smooth, connected, projective curve over C of genus G. And then in this category, we declare morphism between these two complex curves, C and C prime, to simply be an isomorphism in the category of schemes over C from C to C prime. So it's a groupoid by definition. We're declaring morphisms to be invertible. And in our second example, it's sort of, I want to view every set as a groupoid. So if sigma here is a set, we define the category C sigma as the category where objects are elements, X and sigma, and you only have the identity maps. So in this way, you can view every set as a groupoid. And then what I've written here is I've tried to highlight that, morphisms, first of all, morphisms of groupoids are just going to be functors of categories, and equivalences of groupoids, or like isomorphisms of groupoids, are going to correspond to equivalences of categories. So as an example of equivalence of categories is what I've, on the left-hand side, I have just two objects, and then I have two maps, which I call 1 and -1, between any two objects. And so in particular, X1 and X2 are isomorphic, but yeah, in two different ways. And this groupoid is then equivalent to the groupoid where you just have one object and two maps, right? Like if you think about this map is fully faithful and essentially surjective. And in a similar way, let me just draw maybe another example. Let's consider a category with 4 objects. And so I have the identity maps. And let's suppose I have unique maps going here, 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 and here. But then no maps between these 3 objects and the 4th one. Then this is going to be equivalent to the set of just 2 points. Right, and this category, this one is equivalent to a set. So we say a groupoid is equivalent to a set if there's some set out there and equivalence of categories between C, sigma, and that category. And so you see on this left-hand side, this is not technically a set. It's not equal to a set, but it's equivalent to a set. Great. And now, moving on. Okay, one very important example of a groupoid coming from geometry is the moduli groupoid of orbits. Here, G is just an abstract group and acting on a set. And we're going to define this quotient groupoid as a category where objects are, again, elements, and then a morphism from 2 different elements of the set are going to be all elements of G that send X to X prime. And so this you could just check as a groupoid, and maybe as an exercise, show that this is equivalent to a set. Equivalent to a set if and only if the action is free. It's useful to play around with the concepts. All right, and now we turn to a really important special case of this, which is the classifying stack. And this is the special case where you take the action on the 1-point set, and then you get, this gives you the category BG. And this category has like 1 object. And then morphisms from this object to itself is given by the group G. So this is the classifying stack, but without, this is still, just a groupoid. We haven't given it a geometric structure. We're gonna endow all of these with algebraic structures later. Well, as long as G and the set, if you have an algebraic group acting on a scheme, we'll be able to view this geometrically later. And maybe just to give some more examples, let's just consider a quotient. Let's suppose you have a quotient of groups, Z mod 4 to Z2. So in this way, you can view Z4 acting on Z2 via this group homomorphism, and then this groupoid. Then if you look at this groupoid over here, this would then be equivalent to the quotient Z mod 4 mod Z mod 2. And on the other hand, this would be equal to B of the classifying stack of Z mod 2. Or more generally, you could try to show that if you have any surjection of groups, then the induced action, then the quotient groupoid is going to be the classifying stack of the classifying groupoid of the kernel.
On the left there, Jared, is that Z mod 2 mod Z mod 4? Or
oh, yes. Yeah. Yes, I wrote it the wrong way. Thank you, Hannah. Yeah, here. Yeah. Oh, yeah. That.
Would you say you got it right up to a Z mod 2 equivalence? Sorry, just couldn't help it.
Oh, yeah, great, thanks. And yeah, and then as the last example, and this one appears in representation stability, it's kind of interesting, is if you take, let's let FB be the category of finite sets, where morphisms are bijections. So this is also a groupoid. And if you think about what this is, this should be the disjoint union over all positive or non-negative integers of the classifying stacks of the symmetric group. Right, so yeah. So even before we get to prestacks, I really think it's nice to think about groupoids geometrically, and other constructions of prestacks are maybe most easily viewed in the first case, in the case of groupoids. So for instance, for fiber products, I think before we jump to fiber products of prestacks, well, okay, I haven't defined prestacks yet, but I think this is the simpler case to consider first. So let's spell out what fiber products of groupoids are. So let's suppose we have a diagram of groupoids, and F and G are functors of groupoids. And we're going to define a category, which should be the fiber product, as follows. So objects should be triples, C, D prime, alpha, where C should be an element of C, D prime should be an object of D prime, and then alpha should specify an isomorphism between F of C and G of D prime. This is different. This is an added level of complexity to, fiber products of sets or schemes where you're just parameterizing, elements C and D prime that agree in D. But now, since these are categories, we shouldn't say agree, we should say isomorphic, and then we should include that isomorphism as part of the data. And then to spell out what morphisms are, so a morphism, can say C1, D1 prime, alpha 1 to C2, D2 prime, alpha 2, should then be the collection. First, you should have an isomorphism from C1 to C2. Let's call that beta. And then you should have an isomorphism D1 to D2 prime. Let's call that gamma. And these should satisfy some sort of compatibility condition. So beta is an isomorphism in C, gamma is an isomorphism in D prime. So we could take their images, right? If I take F of C1, that maps via F of beta to F of C2. And I could also take G of D1 prime, that maps to G of gamma to G of D2 prime. And remember, alpha 1 and alpha 2 are these maps. And what we require is that this commutes. So this constructs a category here, and it fits in this diagram as follows. You have C cross D, D prime, and you have projection morphisms, P2 to P1, which are, are clearly definable at least. And in this case, I would urge you to try to think about what is the universal property. I'll spell out a universal property in the case of prestacks in a moment, but I think I would urge you to try to think about what it should satisfy, because there's a lot here. We're getting into some of the new technical difficulties dealing with categories. Right, and then if you do have this as a fiber product, you'd want to say that this is a Cartesian diagram. So let's think about some examples. Maybe the first example I like is taking BG, so the classifying groupoid of an abstract group, and then you have these morphisms from a point, right? This is just, we're viewing this just as the category with one object and one morphism. And the fiber product, well, actually, if you look at the definition, you know, an object should be an element here, there's no choice. An element here, there's no choice. And then the choice comes to an isomorphism, which is just an element of G. And if you work it out, that's exactly what the fiber product is. So this is an example of a fiber product. And maybe as another example, let's consider let's take a group G acting on a set sigma, and let's take an element of sigma. And so, yeah, and there's two notions here. You have the orbit Gx, and then the stabilizer G little x. And there's a morphism from the classifying stack of the stabilizer into sigma mod G, right? Where this just sends the unique point to X and morphisms yet to morphisms. And if I take the projection from sigma to here, what is the fiber product? And maybe as like an exercise, I would encourage you to try to check that it's actually the orbit.
So to clarify, like when you say that the stabilizer or the orbit or the group is a is the fiber product, do you mean like the discrete groupoid on that set?
Yes.
Okay.
Right. Yes, that's a good point. Grant has raised this point that yeah, I'm sort of systematically using notation in the class, and we're building more and more structures. But all of the earlier structures are going to have the newer structures, and we're always just like viewing it. So like, if you even look in this, in the first example, a point to BG, or in the sigma to sigma G, when we view this, we view this, you know, as the category associated to the set, and then this is then a functor between it, right?
So,
and same with this.
in the first example then, like, is the G in the top left supposed to be the same thing as BG?
No, yeah, this should be the BG, and this here you drop the B, it's just the G.
So then how do we consider, never, I see. So we're considering the category where like the objects are objects of G, and then we only have identity?
Yeah, exactly, yeah, good point, yeah. So this G as a category is elements of G, but you like forgetting the group structure at all, and then the only morphisms are the identity.
Okay.
Yeah. Other questions?
Yes. Is what you define the fiber product in the category of groupoids?
Yeah, that's the question. That's the exercise for you, is to work out a notion of a fiber category in the category of groupoids, and show that it satisfies it. Yeah, you can here. I don't want it yet. You can formulate what it means to be a fiber product in the two category of groupoids, but I'm not. Yeah, I'm avoiding that. Oh, it's an exercise. Yeah.
Okay.
But we'll approach this again later when we discuss prestacks. Right. So here we go. But I'd like to first start with some motivation for prestacks quickly. And to begin with, let's just recall what is required in specifying a moduli functor, right? To specify a moduli functor, you need to specify families of objects over any scheme. And then you specify when two objects are isomorphic and how families pull back. So the main difference here between a moduli functor and a moduli prestack is just changing the when to how. That's the only difference. So we now don't want to know, like, we don't want to just give an equivalence relation on families. We want to remember the equivalences. Great. And so, yeah, so let's give a first attempt at trying to define a prestack. And so maybe the most natural thing to do is just to consider maps or assignments from the category of schemes to groupoids rather than to sets. Let's call this map F. But if you pause and think for a moment, this isn't an ordinary functor because we're mapping to groupoids, and an object of this category, a groupoid is a category itself. So this is really a category of categories, or a category enriched in categories, where the morphisms themselves have the structure of categories. And so this is a notion of a two category. And again, I don't want to really dwell with two categorical issues. But yeah, so but nevertheless, if you had such an assignment, you can think about what does it entail. So how can we write down such a map or such an assignment? And so the first thing you need is that for every scheme, S, you should have a groupoid, Fs. And then, like functors, we should have pullback maps. For each map, say from a scheme S to T, given by a map F, there should be a pullback map from F of T to F of S. And then usually with functors, you acquire a condition on a composition of morphisms. So if we have S to T to U, this is F and G, you can consider what happens if you pull back first along G and then compose with the pullback of F. And with functors, you just declare that it's equal to what happens when you pull back along the composition. But here we can't say, or we don't want to say equal, so we'll say that they're equivalent, that there's an isomorphism of functors. And let's specify the isomorphism as C, F, comma, G. And now, is this enough? Well, no, because of some categorical issues, right? Now there should be a compatibility condition on these maps for triple compositions. But I'm not going to spell it out. I'm not formally introducing a definition here, but I'm just trying to motivate a concept. Really, what this leads to is a notion of a lax or a pseudo functor, or I think lax two functor. But I did want to point out that already. This kind of seems kind of complicated to describe a new geometric object this way, where you have to give groupoids, you have to give pullback maps, you have to give compatibilities, and then you're carrying around all these isomorphisms with you as part of the data. And this is just to describe a single object. Now, if you want to describe a morphism between them, you'd have to, everything would be sort of formulated in terms of these isomorphisms, and you can see it gets kind of nasty. You can work with this category, and it is a conceptual way to think, but we're going to instead take a different approach. So actually, instead, what we'll do, introduce formally on the next page, but here still as motivation. Instead, what we do is we build a massive category, X, with all of this data. So here X is going to be a category, and it's going to live over the category of schemes. And an object of this category, in the setup where an object should correspond to like a scheme S and an object. So this S is a scheme. This A here is an element, let's say, of F of S. And then this object lives over the scheme S. And we're going to formulate things in this way. So rather than considering these assignments, essentially what we're doing, you could think that we're building X as this union over all schemes of these fibered, of these groupoids FS. That's the way, the way we think of it. But yeah, and so this is the way we'll define a prestack. Okay. I'm going to pause for questions and then move to the next slide.
So just to be clear, this notion that you're defining is not the same as just a functor from schemes to groupoids. This is more data, right? Or is it?
Well, no, I wouldn't say it is. And in fact, if you define pseudo-functors properly, you can even say there's an equivalence of two categories between prestacks and these gadgets. You can, but making that precise is a lot of work, and I'd rather like sort of I'm not going to try to prove something like that. I'm just going to systematically work with these prestacks. And I view it as the same amount of data. Yeah, it's not really more data. It's just like the union of all. Yeah, I really think of it as the union of all of the objects.
Cool. Thanks.
And then one of oh, sorry, I just want to.
Go ahead.
And then one of the like crucial instances of this is when T and S are the same, right? That's like, I just want to make sure I'm understanding the motivation correctly. Like the point is that we're worried about automorphisms of some curve.
Mm-hmm.
So if T and S are the same, then we're keeping track of how S map to itself in some sense, right? So we're sort of like augmenting the category with this extra information, right? Alpha.
Yeah, I think that's a good way to think about it. Yeah.
Okay.
And so in particular, like in this category X, you can have morphisms that live just in this F of S, so there'll be morphisms over the identity. But but there's also, you need to be able to compare objects over two different schemes, S and T.
Okay.
Yeah.
All right. Yeah. Thank you.
But yeah, let's define it precisely. I think maybe you've had enough of this motivation. Okay. So we start. So here S, we're thinking is the category of schemes, but in this case, there's no topology. It can just be an arbitrary category. And then we're considering a functor, so a category X together with a functor to this S, this script S. And this is sort of just how we visualize this data. These here, these A, the A and the B are like objects of X, and these things here are objects of the base. And then we say, for instance, that we say that A is over S, and that the morphism alpha is over the morphism F because it projects under P to that. So that's how we think of this. And now a definition of a prestack is really two conditions. It's one, that pullbacks exist, meaning that for any diagram over here, So so in other words, like if you have a morphism from S to T and an object B over T, the conclusion is that there exists a map A to B over S to T. And these pullbacks need to satisfy a universal property. I mean, it's sort of like a fiber product, but since it's a little more general since we're over an arbitrary base. So the way we formulate it is to say that for any, this is down in this picture here, is that we're saying this is the universal property for B being a pullback of C. And the condition is that for any other object A over some object R, that and a map to C, then there exists a unique map here in this dotted map. So that's all it is. Pullbacks exist and is a universal property. In fact, if you think about what this condition 2 is saying, it's actually saying a little bit more. It's also saying that every arrow in X is a pullback. So it's not, So it's in a different language. I mean, you say that a morphism B to C satisfying this property is Cartesian, and then and then we're requiring that every arrow in the category is Cartesian. There's this intermediate notion that I won't introduce of just a fiber category, which is but I don't think I don't think it's relevant really to think about it at first. So here we just have a prestack. Pullbacks exist. Every arrow is a pullback, and you have a universal property. That's the definition. And maybe to highlight, I was sort of in the motivation sections in the first 2 lectures, I was emphasizing this perspective that a lot of the background material can be sort of black boxed. You can just package results of descent or an approximation. But the formalism of prestacks is absolutely necessary if you want to go further in this class and work with stacks. It's like developing scheme theory and not being able to really work with sheaves. These are like the fundamental gadgets that we'll be studying, and I would urge you to just start to play around with them, work out fiber products, and do some exercises. Anyway, okay, that's the definition, but I have a couple remarks I want to make. First is that this sort of is a warning, is that this is not standard terminology, unfortunately. I would argue that it should be, but these are usually called categories, fiber, and groupoids. Which is sort of a mouthful, both to say and write. So I'll use the prestack terminology.
Jarod,
And unfortunately, the term prestacks do appear in the literature. Actually, they're defined in Olson's book as well as Vistali's notes, and they mean something else. There's actually an additional axiom where it's one of the stack axioms for morphisms is imposed. So I'm just warning you to be careful.
Jarod,
with how this word is used.
Jarod, I want to make a comment, but I'm not sure what to say other than I really strongly agree with you that, but I don't know whether, this is the thing that really should have been called prestacks. I don't know whether people are going to get very upset or confused, but I really think I agree with you. I just don't know whether people will be upset with you.
I'm kind of curious. I hope, let's start a movement to call them prestacks.
Okay, I'm with you.
I checked the stacks project. Prestack is not defined anywhere there, so we're not.
Thank you.
Can we call that other thing a separated prestack then, and then that would be consistent?
Well, the one problem with that is that there are there's only 2 steps to get from a pre-sheaf to a sheaf, but there are 3 steps to get from a prestack to a stack, from a Jarod prestack to a stack.
Yeah.
It's a third.
Semi-separated prestack.
So, the other thing I want to point out is sort of this abuse of notation that is often comes along. That we often only write x, not, the functor from x to s. So for instance, when defining prestacks, we often just write what the objects of of x are. It's usually completely clear what the projection functor p is, but we just drop it from the notation. And we often, when defining prestacks, we often don't spell out the composition law, even though that's an important part of the data. But then in all the examples, I'll give, or in this course, it's transparent what the composition in the category should be. And finally, this convenient notation for police pullbacks, F pullback B, F restricted to S, is one way to say that, that is to denote it's really a choice of pullback.
So I really want that that arrow in the universal property to be unique. That's correct?
Yes, it's unique. Yeah.
And I so you're kind of abusing notation and writing these vertical arrows as if they were morphisms, even though it's just mapping an object down with the functor. Yeah. And that's a nice picture, but if I was going to imitate the picture of a pullback, then I wouldn't have A sitting over R. So I would just have A mapping down to S. So is that necessary? Why is that necessary?
Well, that's sort of the condition. But if you drop it, if you just had A, what do you mean in that from A to S? Yeah.
I mean that the way that the universal property of pullbacks is usually stated is you take another diagram that looks like a pullback, that is a square. You take another square that commutes.
Oh, I see. So you're
and then there's a unique morphism from one
so
square.
like in this case, you might have some A prime over S. Yeah, so that would be like the ordinary way to specify what a fiber product is. But yeah, because we're over this base, it's just a stronger condition and one that we want to impose to declare that to work in this more general setting where where this object may not live over S, but some other thing.
Okay, thanks.
Yeah, you just view it as it's a slightly stronger property that we'll need. And the final thing on this page is this important notion that if you have a prestack, you define the fiber category, which is this XS, where it's the category where objects are just objects of X that live over S, and then all of the morphisms are over the identity. And as a useful exercise, you should show that that if you have a prestack, then all of these are groupoids. That every map in the fiber category is invertible. All right, let's turn to examples because I think that's really the way you really immerse yourself in the material. So now I'm a sequence of examples, and I'm going to first start, by showing how presheaves can be viewed as prestacks. In all of these examples, we're going to take S to be the category of just of schemes. So we have, suppose you have a presheaf F, and we're going to build a category XF as follows. Objects are just pairs, where S is a scheme, and A is an element of F of S. Kind of like what we had before. And then a morphism between these pairs is going to be a morphism of schemes such that A is the pullback of B. And so what this gives us is we have XF And here the projection to schemes is, it just sends a pair to the scheme. And so this is the construction of the prestack affiliated to presheaf. And we often conflate F and XF, like we've been doing with every other object, right? If I have a presheaf and it's mapping to a prestack, then you have to view that presheaf as a prestack itself. So that's presheaves. And moving on to example 2, schemes. Well, we've already seen how you can view a scheme as a presheaf, and so bootstrapping on that, you can view a scheme as a prestack. But since it's such an important example, let's spell it out here. So let's let X be a scheme. And so you build the category. You build the category X with respect to the scheme X, and an object is just a map from a scheme S to X, where S is not fixed. It's maps from all schemes to X. And then a morphism, say from S to X, T to X, is going to be the data of a morphism from S to T over X, such so that this diagram commutes. And then, so this gives us a prestack over the category of schemes. Again, where this gets mapped to S.
Sorry, don't we only want to include isomorphisms here for our definition of prestack?
Well, yeah, but this is, yeah, right. No, you're right, but here we're varying S and T. So yeah, so it's not true that all morphisms in the category are isomorphisms. But if you think about what are morphisms over the identity in this category, well, the morphisms over the identity, so the map from S to T must be the identity. Like, so in other words, yeah, it's.
Oh yeah, I see. I think
right, like in this projection functor here, this morphism, this is a morphism in the category X, and it projects to the map S to T. Yeah, so the only morphisms over the identity are the identity, so to speak.
So would it be correct here to say that you're making a sheaf as a category fibered in sets?
Yes. Exactly correct. Yeah. You can view a that's a good way to view it. You can view a presheaf as a category fibered in sets. People, yeah. There's also this notion of setoids, which might be like a groupoid equivalent to a sets, yeah, that's a good way to view it. Yeah, but now turning to MG, this is our primary example in the class, and now we're defining it as a prestack. So MG as a prestack has objects are just families of curves, families of smooth curves of genus G, where S is a scheme. And then you declare that a morphism from C to S to some C prime to S prime is the data of, well, first you should have a morphism S to S prime, but you should also have a morphism from C to C prime. And not only should this commute, but this is Cartesian. So you're declaring that this is Cartesian as part of the data. And since and this is what is forcing it to be a prestack, or that the fiber categories be groupoids, is because you're declaring, that this is Cartesian. And so if you think about the special case where S is the spectrum of a field, say the complex numbers, then your objects are smooth, your objects are smooth complex curves, and then your morphisms are, well, morphisms say over the identity, so it should be maps from one curve C to C prime. But for that to be like Cartesian over the spec of the complex numbers, that map better be an isomorphism. So this is why the fiber categories are groupoids. And okay, and moving on now to vector bundles. So let's define the prestack of vector bundles over a smooth connected projective curve. So here we fix C once and for all, and now we're going to consider objects are going to be pairs consisting of a scheme and an F, where F is a vector bundle on C cross S. And then a morphism, say from S, F to S prime, F prime, is going to be the data of a morphism of schemes, so S to S prime. And then you should also have an isomorphism. And maybe an isomorphism between the pullback of F prime and F. So this is part of the data, an isomorphism. I think maybe some of you might object at this point because sort of we want to do everything in a canonical way, but when you write this here, this requires a choice of pullback. Which pullback is it? Well, a better way to write this maybe is part of the data then is actually a morphism F prime to the push forward of F cross I identity, such that the adjunction map is in ISO. Anyway, that's a technicality. I mean, but that the push forward is canonically defined while the pullback is not, and so you can just declare that a map to be a morphism from F prime to the push forward, such that the adjunction map, which is over here, is an isomorphism.
So there was a choice of pullback in your example 4, but not in example 3. Could you just say like you're saying like? Could you just explain that a little more?
Well, yeah, I guess in example 3, I'm not. So I'm declaring what a morphism is between two families of curves, and so I haven't made a choice of a pullback of C prime to S. I'm just declaring it a map to be a morphism, such that the corresponding square is both commutative and Cartesian. Does that help?
I think so. So it's so long as that square satisfies some universal property about maps to the two other things, then, but like, is it the same as, like, could I think of it as, well, there is something that I could define to be the pullback, and then you gave me an isomorphism of the C with the pullback along that thing, or?
No, yeah, that's exactly right, Hannah. Yeah, you could also do it that way. Like if you wanted to make a choice of the pullback of C prime to S, then the data would be like an isomorphism then of C with this chosen choice of pullback. So yeah, that's the way, a good way to think of it. But yeah, when you write things down formally, you often want to avoid choices.
Thanks.
And as our final example, I want to define the quotient prestack. And so here, okay. Here G, let's let G be a group scheme acting on a scheme X over S. So I'm here, if you want to take S to be the complex numbers, that's fine. Here I just do everything relative to scheme S. And then an object, okay. Oh yeah, an object then is going to be, an object of this category is just going to be a map from T to X. And so this is actually going to live over the relative site, schemes over S. So this is a map over S. Everything is over S. And then a morphism from T to X to say T prime to X. Well, what should this be? Well, there's two different maps here. I think. I should have. Well, the first thing I should have is a morphism T to T prime. But then I can compare these two compositions. I have on one hand I have T to T prime to X, and I also have just T to X. And I want to say that these maps are equal. So that part of the data is also an element G of G of T that sends one to the other. Okay, this is a lot to unpackage here. So first, I'm working in the category of schemes, and I've used the notion of a group scheme and an action of group scheme. So if you're unfamiliar with that, I urge you to look it up. And I'm also viewing this sort of functorially. From the functorial perspective, a group scheme is just a functor that factors through groups, like with a choice of factorization through groups. And so here, so in other words here, G of T acts on X of T. And then, so then a morphism then is sort of like what we considered in the moduli groupoid of orbits. A morphism is then the data of an element functorially that sends one morphism to the other. That's all it is. So I'm going slower than I thought I would have, but I think that's good because material is really important. I guess I want to, I'll present one more slide. I won't cover everything I plan to. So I do want to talk about morphisms of prestacks, and then we'll probably call it a day.
Would you mind saying in words what the set of morphisms are on the previous slide?
In words, yeah. Right. So a morphism from a map T to X to a map T prime to X is the data of a map from T to T prime, and then an element of an element G of G of T. In other words, a map from T to G, which takes like one of the composition to the other one. Yeah, so maybe it's always easier to describe what the fiber categories are. So and maybe let me highlight that here. So if we go up here, maybe as an exercise, show that if I take X mod G pre, and then I take the fiber category over a scheme T, show that that's the same as the quotient groupoid of X of T mod G of T, where this is just the quotient groupoid. And so the case of describing the morphisms over the identity, so like where T prime equals T is sort of the simpler case where it's easier to grasp what's going on. All right. So I cheated here and wrote down a lot on the left-hand side, but I'll describe it. So a morphism of prestacks is the main definition here, and it's just a functor, but we require that this diagram strictly commutes. In other words, if you have an object A here, this means you actually have an equality between the projection of A and the projection of the image of A. And so I know we're told and taught not to use equals, but here we do. And since we're in this larger, since we're now working with prestacks rather than pre-sheaves, if I have two morphisms, I can talk about what a two-morphism is, right? Because a morphism is a functor, and so you could say then this is a natural transformation. So a map of functors. And we use this is sort of a diagrammatic way of representing that data. This is, alpha is called like a two arrow, a two morphism. Great, so now if we fix two prestacks X and Y, we actually get a category of morphisms, right? Where the objects are morphisms and the morphisms are two morphisms. And maybe as a simple exercise, show that if you have prestacks, then this category itself is a groupoid. And due to this extra two-level structure that we're dealing with, we also need to change our notion of commutativity, because like if you look at this picture here, you can compose in two different ways. And so you have these two functors, like two different maps from this to here, and we don't always want to declare that they're equal. So we say that a diagram is two commutative if there is a two isomorphism between their compositions. And the two isomorphism is part of the data of a two commutative diagram. And then finally, an isomorphism is simply a map with an inverse. And you can, and maybe as another kind of exercise to play around with the notions, show that X to Y is an iso if and only if all the maps on the fiber categories are isos. Great. Okay, this was a lot to say, and what I want to end with is the two categorical version of Yoneda's lemma, which I've spelled out here. And so for whenever you have a prestack over a category S, the claim is that there's then a natural equivalence between morphisms now this is a category of morphisms and the fiber category. So the claim is that this is equivalence of categories. And I don't have that much time, but I at least want to point out how these maps are defined. So first, remark here that if you have a map from S to X, this is a morphism of prestacks. So here you're viewing this as a prestack, viewing the scheme as a prestack. And so, so what is that? What is involved in giving such a morphism? Well, a morphism of prestacks is a functor. So for what this means is that for every scheme T, we have the objects of S over T are all morphisms from T to S. So this is the map F over T. And this should map to X of T. And again, and so if you take T to be S, the identity of S lives here. And so this does map to F of S, identity of S, and this is an element of X of S. So what I've done is really just to describe this map. And I'll end with a quick discussion of a construction of the inverse. Let's construct the inverse. And let's just suppose we have an object, A and X, over S. And so what we do is for each, say, map from T to S, say G, make a choice of a pullback, G pullback A. And then we define F from S to X. Well, by defining, we need to define FT from morphisms from T to S to X of T. And here we send a morphism G to the chosen pullback of A. Okay, but this is okay. You also need to also define it on morphisms, and the details are all yours. I can't write down there. Yeah, so I'll leave all the details to you, and I think it's again, this is a case where it's better if you work it out yourself. And so next time I'll give a quick recap, and then we'll move on to fiber products of prestacks. I'm going to end the recording now, and we can have a very quick, maybe 5-minute discussion.
Question on the